Assalamualaikum warahmatullahi wabarakatuh, and hi to everyone. So in this video, we continue with our discussion of a transmission line model, and here we start with, or we proceed with the part 3 of the discussion on the medium transmission line, and we begin with the definition, where basically the transmission line for the medium distance is defined in between 80 kilometer up to 250 kilometer. So we have seen the short transmission line, which is covered from 0 up to 80 kilometer, and now we move on to the second part of the transmission line, namely medium line, and it is covered from 80 kilometer and then up to 250 kilometer. So we do have the shunt capacitance, which has been neglected in the short line model, but taken into consideration this time around. So included and divided into two equal parts placed at the both sending and receiving ends of the line to form the so-called nominal phi model. Okay, so this is the alienation part of the medium transmission line. Okay, we have the shunt capacitance. Okay, and here the total shunt admittance, okay, is given by y equal to g plus j omega cl. Again, this is the distance of the transmission line in kilometer. So g, this is the conductance, the shunt conductance of the shunt admittance, where this is actually the inversion of R, okay? Or ohms, okay. So shunt conductor per unit length, G is negligible. Okay, so by the way, G equal to 0, it is negligible in medium line, but C, the line to neutral capacitance kilometer, is calculated. Okay, so we have C, we have omega, so we have J as well, and also the L. Okay, and then this is the relationship if you refer to the equivalent circuit over here. So we can analyze, or we can come up with this equation: IL equal to IR plus Y over 2 VR. Okay, so this is the admittance. Okay, over here, okay, these two. So we can say that IL here is equal to IR plus Y over 2 VR. Okay, you can see from here. So this is the point where you can apply KCL. Okay, so we have KCL over here, the current Kirchhoff law. So now we have seen two branches of I, okay, as the output of the IL at this branch. Okay, the KCL of node A, for example. Okay, so one to the right and one downwards, okay, to the bottom of the circuit. So we have IL equal to IR, okay, plus VR, so the Ohm's law, so VR multiplied by Y over 2. So this is the inversion of the ohms. So basically we have V over R, but in this in the admittance or conductance, we have V multiplied by Y over 2, okay, as the result of V multiplied by this is Y, okay, over 2. Okay, the same thing actually here. And then from here, okay, this is similar. So similar as what we have seen in the short model. So Vs equal to Vr plus ZIL. So we can see from this relationship. Also we have Vs over here. So we have this one, IL multiplied by Z, as well as the VR. Okay, at the receiving end part. And then rearrange how? So we have the relationship IL equal to IR plus Y over 2 VR into this into this IL. So everything here IR plus again Y over 2 VR over into this IL, and rearrange, you may get this relationship. PS equal to 1 plus ZY over 2 VR plus ZIR. Okay, so the IR and the VR. Similarly, this is for IS, descending, descending I, okay, here at this point, let's say we have a point on node B, so we try to apply KCL at point B, so we have this current downward, okay, which is equal to Vs, this current equal to Vs multiplied by Y over 2, okay, the inversion of R or ohms. This is y over 2, and then this current to the right is IL. Okay. Then we have IS equal to IL plus y over 2 Vs. And you see this Vs, try to substitute all these, okay, into this Vs. And rearrange, you may get in terms of again VR and IR. Okay. As well as this IL. Okay. So now into this IL. Okay. So we have IL, which is being replaced by this equation, and Vs, which is being replaced by this equation. So leaving the constant of IR, VR, so VR, IR. Rearrange, so you may have VR and IR relationship. Okay. And from here, I believe you can actually have the parameter of A, or you may represent the parameter, okay, by A, B, C, and D. Just like we have in the short transmission line model. Okay. So representing the two-port network, okay, the two-port network over here, the port network A equal to 1 plus ZY over 2, so B equal to Z, C equal to 1 multiplied by 1 in bracket, so 1 plus ZY over 4, and then D, this is equal to A. Okay, this is equal to A, we have 1 plus ZY over 2. So A and D are dimensionless, so with no unit for A and D, because they cancel out each other by multiplying Zn between Z and Y. Okay. Similarly, so analytical operation for D, so they cancel out each other after we multiply Z and Y. Okay, because this is ohm actually multiplied by mho. Okay, multiplied by mho. Or we can say that this is actually ohm multiplied by 1 over ohm. Okay, so ohms, not ohm, so that means so no unit or dimensionless. Okay. If the line is the same when viewed from either end, so regardless where the line you are view from, so either sending or receiving end, so the dimension are still 0 or less, and they are equal in equation. So the dimension B and C are ohms and mhos. Yes, this is ohm Z. Okay, so this is C, this mhos. So mhos, because this is, even though this has been cancelled out each other, but you still have Y, okay, as the unit or the dimension. So you have more over here still remaining, and this is obviously ohm. So the determinant of the line matrix is unity. Okay, AB, so this is the determinant AD minus BC. Again, determinant of the matrix, the line matrix is equal to 1 or unity. So we can find VR and IR if ZS and IS are unknown. Okay, so VR, so try to arrange the equation. Okay, in terms of this parameter A, B, C, D. Okay, we may get VR in terms of Vs and Is. Okay, similarly for IR, rearrange the equation, so you may get the relationship in terms of Is and Vs. So rearrange again, this is VR equal to dVs, okay, minus Vs, Bis, because you know that this is the determinant of the matrix, and this is equal to unity, this is equal to 1, and this is equal to this is equal. So leaving VR equal to dBs minus BIS, IR equal to AIS minus CBS. So in matrix form, the inverse matrix, because just now in the short line we have V in term of VS, but this time around we have the inverse matrix in term of VR and also R, means the receiving end part. Okay, previously we have seen, so everything is represented in terms of sending quantities V and S. So we do have D minus B, okay, second parameter, and then the third parameter we have A and minus C over here. So make it reverse inverse, sorry, and then we have D minus B, so negative C, and also A for IS. Okay. Right, then what happened during the no load operation? So if the system is run at no load, so i.e. IR is 0, yes, this is the condition under no load operation where we have IR equal to 0 ohm ampere, sorry. So thus A is the ratio between Vs and VR. Okay, so we can see from where is it? This one. Okay, so whenever the value of IR is 0, so rearrange, so we can see that A is actually the ratio between Vs over VR. So is the receiving end is short circuit. So the end part of the circuit of the transmission line is being short circuit. So VR equal to 0. Okay. So no load mean open circuit, IR equal to 0, but short circuit, so we have a straight line over here. So we have VR equal to 0 volt. And thus, again, from this expression, since we have VR equal to 0 volt, so rearrange, and we can get the ratio Vs over Rs is actually defined by this B. Constant A is useful. Why? In computing voltage regulation, if VR full load is the receiving end voltage at full load for a sending end voltage Vs, because you know at the equation for VR, again this is equal to VR, this is during no load, okay, so minus VR. So let me write this way, simple way, FL, the full load minus VR, full load 100%. Okay. So we have seen that during a no load where IR equal to 0, okay, receiving current is equal to 0, so this is equal to Vs, the sending end voltage over A. So this is why constant A is useful in computing voltage regulation, okay, due to this relationship. Oops, so this is what I have explained earlier. So we have Vs, the modulus Vs, we take the magnetic value only over A, VR full load over VR full load. Alright, again, thank you very much for your time. So we will see again in last part of the video where we will discuss about the example 7.4, applying the medium transmission line in more comprehensive.